Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And once again, in this hour is your hour. Okay, well, let's move right on. Let's take the first listener phone call.
My name's Robert, and I have a question about parallel universes. Do they see the same sky at night as we do? Thank you.
Well, you ask a very interesting question. It depends on what variety or what theory of parallel universes you believe in. The theory that is most likely to be verified within the next several years to a decade or so is called inflation theory. And inflation theory says that big bangs happen all the time. So think of a bubble bath where one bubble begins to fission off baby bubbles, and each baby bubble is slightly different from the parent bubble. And so the sky that one of these baby bubbles would see looks somewhat like ours, but the laws of physics could be slightly different. For example, if the proton were not stable in one of these other universes, then protons would fall apart into electrons, and we would have basically an uninteresting gas of subatomic particles. Not very interesting. No stable matter, because our universe has a stable particle, a proton, out of which we can create atoms and molecules and you and me. And so, to answer your question, we don't know the answer for sure. We have the Large Hadron Collider in Geneva, Switzerland, which we hope will give us signals from one of these parallel universes. But these other parallel universes could have a sky different from our universes. Instead of stars, they could have gas, or maybe dead stars. In some of these other universes, perhaps the nuclear force is stronger than in our universe, in which case stars burn out very quickly. Or perhaps the nuclear force is much weaker in these other universes than in our universe, in which case stars never ignite at all. So what we need, of course, is hard data, not just speculation. And beyond inflation, we have string theory, which says that even the dimensionality of space and time may be in a parallel universe. String theory allows for the possibility of 10, maybe 11-dimensional hyperspace. And so when children ask the question, if the universe is a bubble that's expanding, children ask the question, well, what is it expanding into? If the universe is all there is, how can it expand into anything at all? And the answer is it expands into hyperspace. It expands into a higher arena. And that higher arena is 10 or 11-dimensional hyperspace, which is the dimensionality predicted by string theory. Okay, well, let's move right on to the next listener phone call.
Chad in Lewisburg, West Virginia. My question is, how do you go from matter being non-living to living? Thank you very much.
Well, you ask a question which goes to the heart of the controversy about biology. Several hundred years ago, people believed in something called spontaneous generation, that life could spring from ordinary inanimate matter all by itself. And to prove that, they did an experiment. Take your dinner table and simply leave it out overnight. Well, the next day, sure enough, there are flies, there are maggots, there are all sorts of insects in your food. And so that was, for many centuries, considered to be a proof that spontaneous generation takes place, that life can spontaneously occur from matter. Simply leave your dinner table out overnight. Well, along comes Louis Pasteur and many of the advocates of the germ theory, and they said no. You do not have spontaneous generation of life. Simply take life, for example, your soup that you had tonight, boil it to sterilize it, and put a cover over it. And then the next day, you'll find that the soup is still fresh as ever. And so spontaneous generation of insects take place because insects land on your food and create eggs. Then the next big jump was when we scientists begin to figure out how this process actually takes place. This was done in the 1950s by a graduate student of Nobel laureate Professor Urey. What he did was an experiment that shook the foundations of biology. He simply got a flask of water, put into it some of the elements that we think were present at the beginning of the earth. he put an atmosphere of ammonia, methane, hydrogen, a real nasty atmosphere, sealed the bottle, and then put a small electric spark. Well, then he walked away. He just walked away from this experiment. A few months later, he came back and he analyzed what was inside the flask, and he found, much to his shock, that he found amino acids. Amino acids are the building blocks of proteins. Proteins are made out of amino acids. And so in other words, he made a paradigm shift. He proved that if you simply get a flask of hydrocarbons, like ammonia, methane, poisonous chemicals, hit it with an electric spark, you get the seeds of life, the precursors of life, amino acids, which are the building blocks of proteins. Since then, we have found amino acids in comets, amino acids in meteorites that have fallen on the planet Earth. And this is now considered to be the best indicator we have of the origin of life. According to this theory, and of course there are variations of this theory, life probably started in the oceans, where there is a liquid called liquid water, which acts as a mixing bowl for DNA and amino acids and proteins. And so you mix all these chemicals together, but you need energy. We think that the original energy of life probably came from maybe volcano vents at the bottom of the ocean. At the bottom of the ocean, we see very hot volcanic vents that release toxic chemicals like methane and ammonia, but also have enough energy to create the first chemicals of life. And so we think that the first amino acids, the first proteins, and the first DNA was created at the bottom of the oceans. But once you have one DNA molecule, it reproduces itself. Then you have two. From two, you have 4, 16, 32, 64, 128, ... And pretty soon, you have chains of DNA giving you the basis of life itself. And then, of course, the DNA had to protect itself, created a cell around it, and that began life. Life that is single-celled, reproducible, starting from nothing. Okay, let's move right along now for the next listener phone call.
Mike from North Dakota. My question is, the Hadron Collider, how will that exactly prove multiple universes? Thank you.
Well, you ask a very interesting question. As I said before, the leading theory that explains the nature of gravity, the nature of subatomic particles, is something called string theory. And you may say to yourself, well, smarty pants, if string theory is the theory of everything, then why don't you guys get the Nobel Prize for string theory? Well, there's a problem. You see, everything has to be verified. You just can't say that, hey, I have the theory of the universe. No. You have to test it in the laboratory. And string theory makes all sorts of crazy predictions. Not only does it predict the subatomic particles that we see today in the laboratory, it predicts whole generations of subatomic particles that we haven't even seen yet. In other words, we can predict what the next batch of subatomic particles are going to be, because these are the predictions of string theory. But unfortunately, the Large Hadron Collider is not powerful enough to test all the indications, the predictions of string theory. Now, the critic of string theory would say, well, the most outrageous prediction of string theory is that our universe is not really three-dimensional at all. Most of us think that the universe is three-dimensional. We have length, width, and height. 3 numbers describes any object in the known universe. But not string theory. String theory predicts that the universe is 10, maybe even 11-dimensional. And that upsets some people, because how do we test this theory? Well, there's several ways of testing it. First of all, with the Large Hadron Collider, we hope to create some of these new subatomic particles which are vibrations in a higher dimension. These subatomic particles are called dark matter. Dark matter, we think, surrounds the Milky Way galaxy. There's probably dark matter in your living room, but it's very hard to detect. It's invisible. It has gravity, but it's invisible. You can't see it. And so we think that dark matter holds the galaxy together. In fact, I think the Nobel Prize will probably be given to astronomers in the next few years who have been able to map dark matter. But we want to create dark matter in the laboratory. We just don't want to conjecture it to be outside the Milky Way galaxy. No, we want to see it in the laboratory. And that's where the Large Hadron Collider comes in. Another way to test string theory is to put gravity wave detectors in outer space. We have now detected gravity waves on the planet Earth. That made headlines a few years ago when that was first discovered. And, as I mentioned, the Nobel Prize will probably be given to those physicists who detected gravity waves on the planet Earth. But gravity waves were also emitted at the beginning of time, at the instant of the Big Bang. So in other words, we're going to get baby pictures of the infant universe as it was created. And maybe we'll see evidence of an umbilical cord connecting the infant universe to a parent universe, a parallel universe. Of course, we don't have this detector yet, but there are plans to launch something called LISA, Laser Interferometry Space Antenna, into outer space, which would have, we think, the capability of detecting radiation from the instant of creation itself. This is truly amazing. Okay, let's move right on to the next listener phone call.
My name is Dylan. I live in Sandpoint, Idaho. I'm calling about time travel and hoverboards because I've watched Back to the Future. I want you to discuss that. Bye.
Okay, well, everyone who's ever watched Michael J. Fox whizzing around the past on a hoverboard has wondered about those two things. Are hoverboards possible, and is time travel possible? Well, let's take these one at a time. First of all, hoverboards. Hoverboards do not exist. You can go to any hobby shop and ask for a hoverboard, and you'll simply get Snickers from the salesperson. Everybody wants to know, is it possible to have hoverboards? And at the present time, the answer is no. Does that mean they violate the laws of physics? No. One day, we may have something called room temperature superconductors. That is, magnets which are superconducting with no resistance at all. The problem is that you have to cool magnets down to near absolute zero before they become superconducting and become supermagnets. Maybe one of these days, maybe somebody that's listening to my voice right now, maybe somebody that's an amateur wondering about that movie, will create a room temperature supermagnet. If you could do that, not only would you be considered the next Thomas Edison, you would also get the Nobel Prize in Physics to boot. A room temperature superconductor. With that, you could probably create a version of the hoverboard in Back to the Future. But at the present time, nope, we can't do it. Now, time travel is much more difficult. So let's say a few things about time travel. First of all, Einstein said that time is a river which meanders its way across the universe, speeds up and slows down. We measure this all the time with our instruments. Time does speed up and it does slow down. But we want whirlpools in the river of time. We want the river of time to take us backwards in time. Well, if you look at Einstein's equations, you see, yes, there are solutions of Einstein's equations which give you time travel. Whirlpools in the river of time. So what's the catch? There's always a catch someplace, right? The catch is you can also use Einstein's equations to calculate the energy necessary to bend time into a pretzel. And it is fantastic. You're talking about perhaps the energy of a black hole, the energy of an exploding star. So in other words, we are far below the threshold necessary to harness the energy necessary to play with black holes and also play with time machines. So sorry about that. Now, however, that doesn't mean that perhaps aliens in outer space that are perhaps thousands, millions of years ahead of us, perhaps they've already been able to harness Einstein's theory to create whirlpools in the fabric of space and time. Now, then the question is, if time travel is possible for an advanced civilization, then why don't we see tourists from the future? That's the criticism raised by my colleague, Stephen Hawking, the physicist. He said that, well, if there are time machines, then where are the time travelers from the future? Where are the tourists from the future? Well, my attitude is that we will probably have invisibility long before we have time machines. So maybe they are invisible. Maybe the time travelers are already here, and we're just too stupid to know it. Perhaps they're already here. And of course, we can't prove it at the present time, but like I said before, it is well within Einstein's theory of relativity, the general theory of relativity, the theory of 1915, to perhaps one day bend the fabric of space and time and leap into hyperspace. Okay, let's move right along now to the next listener phone call.
Why is it that our body temperature is 98.6, and anytime we're in any kind of outside temperature at 98.6, it's extremely uncomfortable? Thank you.
Okay, well, it has to do with evolution, because for most of the history on the planet Earth, perhaps animals were not warm-blooded. We're not sure, but there is a theory that says that dinosaurs might have been cold-blooded. Now, let me tell you the difference. Cold-blooded animals, the body temperature fluctuates. Therefore, when they wake up in the morning, they're quite sluggish because it's cold outside. They have to use sunlight to heat up their body temperature, and then they can scurry around in the afternoon looking for food. We are warm-blooded, meaning that our body temperature is the same at around 98.6 degrees Fahrenheit. So why is it uncomfortable for us if we deviate from 98.6? And the answer is we are uncomfortable because our body is telling us something. Our body is telling us that we are ideally suited to work at 98.6 degrees. In other words, it's evolution. Evolution has given us a warning that if we get too hot or too cold, we will die, because we like to have our chemical reactions take place at 98.6 degrees. And why are we here and not the dinosaurs? Because the dinosaurs were wiped out 65 million years ago, probably because an asteroid or a meteor hit the Yucatan of Mexico. Darkening sunlight, temperatures got cold. And when temperatures get very cold, sluggish dinosaurs couldn't forage for food, and so the plant eaters died. Vegetation also died, and then the meat eaters died because there were no plant-eating dinosaurs to eat. So we survived by default. Because we were warm-blooded, we could adapt. We can adapt to cold weather. When we wake up in the morning, we don't have to be sluggish. We can run around like furious mice looking for breakfast in the morning because we are warm-blooded. And if the temperature gets too hot or too cold, there's an alarm system. Evolution has given us an alarm system that makes us uncomfortable if we are too hot or too cold. That's why we sweat. We sweat because the evaporation of perspiration cools us down. And so we have a mechanism by which we can cool ourselves. Also, when we get cold, we get goosebumps. One theory is that we used to have fur, large quantities of fur, and the remnants of that are goosebumps. That's one theory anyway. And the other possibility is if temperature gets too cold, we freeze to death. So, in other words, we get uncomfortable when the temperature deviates too much from 98.6 degrees because it's our evolutionary defense mechanism. Because chemical reactions ideally take place at 98.6 degrees. And when things get too hot, too cold, these chemical reactions shut down. In other words, we die. Okay, well, let's move right along now to the next listener phone call.
This is Mike from Fargo. And my question is, it is said that for the human race to survive, mankind must establish another planet. You think this will ever occur, or is it even possible?
I think it's definitely possible. First of all, I once interviewed Carl Sagan, and Carl Sagan, the astronomer, said we must be a two-planet species. And let's take a short commercial break, but after the break, I'll explain why I think we have to leave the Earth or the human race will die. And then the question is, how will we do it? How will we terraform Mars? We'll say a few things about that after the break. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had this call, will we ever be able to colonize other planets? Well, first of all, we have no choice. According to the laws of physics, the Earth is doomed. You wait long enough thousands, millions, billions of years, and the Earth will die. On a scale of thousands of years, we have to worry about gigantic volcano eruptions, meteor impacts. For example, Yellowstone Park. Yellowstone Park has a gigantic supervolcano underneath, and instead of friendly furry animals, we expect gigantic plumes of hot volcanic ash to be emitted from Yellowstone on a scale of thousands of years, enough to tear the United States of America apart. That's how dangerous Yellowstone National Park is, because underneath is a super volcano. And on a scale of millions of years, we have to worry about gigantic cometary collisions. 65 million years ago, an object hit the Yucatan of Mexico, wiping out the dinosaurs. And then on a scale of billions of years, we have the death of the sun itself. That's right, 5 billion years from now, the sun will die. It will exhaust its hydrogen fuel and then begin to expand, and one day we will have the last nice day. That is, the sun will burn up the entire sky. From one side of the heavens to the other side will be the sun. The sky will be on fire. The oceans will boil, the mountains will melt, and then we will go back into the sun. Now, the Bible says, from ashes to ashes, dust to dust. Physicists say, from stardust we came, and stardust we will return. So in other words, it's a given that we either one day leave the planet Earth or die. Now, Mars is perhaps the closest planet that is habitable. It is a frozen desert. It's quite cold. Atmospheric pressure is only 1% that found on the planet Earth. So we would have to terraform Mars, a process that would take centuries. And how would we terraform Mars? First of all, we would have to raise the temperature of Mars by about 6 degrees. Once we raise it by about 6 degrees, then a feedback loop occurs. We have a vicious cycle. So the hotter Mars gets, the more carbon dioxide and water vapor is released. These are greenhouse gases, and they heat up Mars even more. And so we get a runaway chain reaction taking place. So then the question is, how do we raise the temperature of Mars by 6 degrees? Well, that'll take centuries, and it'll take billions of dollars. One proposal is to send solar satellites, which can heat up the North Pole and the South Pole of Mars, because both poles have plenty of water in frozen form. And so the solar satellites would concentrate sunlight and beam the sunlight down to Mars. Elon Musk of SpaceX believes that we should become a multi-planet species, and he has a more unorthodox way of heating up Mars, and that is with nuclear weapons. He doesn't want to destroy Mars. No, he simply wants to have an airburst over the ice caps to begin the process of terraforming Mars. So in other words, it's not going to be easy. It'll take centuries, but in some sense, we have no choice. Either we leave the Earth and find a new home in outer space, or we die on the Earth. That according to the laws of physics. Okay, well, let's move right along now to the next listener phone call.
My name is Dennis. I'm from Georgia, and I have a question. Have scientists ever answered the question, what came first, matter or conscience? And are they working on it?
Okay, I think you said which came first, matter or consciousness? Well, I think if you were to interview most scientists would say that matter came first. That is, we had the Big Bang, and then we had the stars and the planets condensing out of the Big Bang gas. And then in the planet Earth, we had the oceans. And in the oceans, we had heat in the form of volcano vents that allowed the first amino acids to be created. And out of these amino acids came proteins and DNA, and eventually the first single-celled organisms, and eventually life as we know it. And then life as we know it eventually created humans. Now that's, I think, what most scientists would say. However, since you talk about consciousness, there is a renegade theory that says, no, perhaps consciousness is fundamental to the fabric of the universe. And this comes out of quantum physics. And to be very frank, there's a debate, even today, among quantum physics about the problem of consciousness. Now, why is that? Because when you talk about electrons and subatomic particles and protons, we, of course, are made of them. We're made of subatomic particles. But you see, subatomic particles don't really exist until you make an observation. This is the Bohr theory of subatomic particles, that in order to measure something, you have to have some form of consciousness. Only conscious beings can measure things. And so quantum mechanics tells us that you don't really know precisely where an electron is till you make an observation. But an observation requires consciousness. Consciousness requires, well, things like people. Therefore, this theory says that consciousness is the fundamental aspect of the universe even before the Big Bang. Even before the creation of matter as we know it, it takes consciousness in order to create subatomic particles. Well, what is the other point of view? To be very fact, we're now talking about the greatest paradox in the history of physics. If you want to win a Nobel Prize, try to resolve the problem of the Schrödinger cat. Schrödinger was one of the founders of quantum mechanics. He won the Nobel Prize. He's enshrined in every physics textbook at the graduate level. Schrödinger had an equation, a wave equation, which described the motion of electrons. And he proposed the following. Let's say you put a cat in a bottle, and next to the cat you have a gun. If the gun fires, it kills the cat. The gun in turn is connected to a Geiger counter. The Geiger counter is connected to uranium. When the uranium atom decays, it sets off the gun. The gun then kills the cat. And then the question is the cat dead or alive? Well, that sounds like a stupid question, but in fact it is the greatest paradox in all of science. Quantum mechanics says that before you make a measurement of the cat, before you open the bottle or open the box, the cat can be either dead or alive, or dead and alive simultaneously. What? That's right. According to quantum physics, before you make a measurement, the cat is in a superposition, the sum of a dead cat and a live cat. Now, Einstein thought, this is stupid. I mean, what? You're telling me that cats can either be dead or alive, or in a mixture of the two? And the answer is, yeah, that's right. Because that's how electrons work. That's why we have transistors. That's why we have laser beams. That's why we have Apple computers. All of that depends on the fact that electrons can be two places at the same time. That unless you make a measurement, you don't know where the electron is. So this is a theory that cannot be dismissed. It was pushed by Eugene Wigner, winner of the Nobel Prize, and also one of the creators of the atomic bomb. And even today, we have physicists who debate the question. Now, let me answer my point of view on this question. My own point of view is something that's even weirder than the above theories that I just mentioned. It's called the many worlds theory. Many of my friends believe in the many worlds theory. They're Nobel laureates that I've had on Science Fantastic, in fact, like Frank Wilczek of MIT and Santa Barbara. The question is, how do you reconcile the fact that electrons can be two places at the same time? The answer is, the universe splits in half. That's right. In one universe, the cat is dead. In the other universe, the cat is alive. The whole universe splits in half. In fact, it is constantly splitting in half. Now you may say to yourself, that's really weird. Starting from a point of view that consciousness preceded the Big Bang, we now have an even crazier theory that we have multiple universes. Well, ultimately, it comes down to experiment. Experiment says that quantum mechanics is right. Tough luck, kid. Hey, you don't have to like quantum mechanics. It just is. It is the way electrons behave. Electrons can be in parallel universes. Either that means that consciousness precedes reality, or it means we live in multiple universes. Believe it or not, this is the greatest paradox in all of science. If you can resolve it, perhaps you will get a Nobel Prize. Okay, well, unfortunately, we just ran out of time. Unfortunately, that's it for Science Fantastic. Once again, you've been listening to Science Fantastic with Professor Michio Kaku. Join us every week when we discuss the cutting edge of science.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to take your listener phone calls. Let's take the first listener phone call.
My name is John. I'm from Vancouver, Washington. Animals give off heat. Do plants also emit heat? Thank you. Have a good evening.
Well, most of us would probably say no, that plants do not give off heat, but the answer is actually yes. Plants give off a very small amount of heat which is actually measurable. And why is that? We have something called the second law of thermodynamics. Now, that doesn't flow off the tongue very easily, but it's one of the most important laws in all of physics, the second law of thermodynamics. There are many ways to express it. One way to express it is to say that everything rusts, everything gets old, everything falls apart, eventually everything decays. In order to reverse that a little bit, you have to add energy. But whenever you add energy, it creates waste heat. And so plants move because, of course, fluids move inside the plant. And the second law of thermodynamics says that whenever you have motion, it takes heat to create that motion. And so, yes, plants don't move very much. In fact, plants hardly move at all. But water within the plant moves, and it takes work to move the water inside a plant. And that means heat is generated as a consequence by the second law of thermodynamics. Now, this has implications in our life, the fact that heat is always generated when you have mechanical motion. For example, in a hot day, what's the first thing you do on a hot day? Well, if there's no air conditioner, you grab a fan. You grab a sheet of paper, anything to cool yourself off. But then the question is, does that really cool yourself off in the long term? And the answer is no, by the second law of thermodynamics. First of all, when you fan yourself, you feel relief. And that is worth it, okay? The emotion of relief. And why is that? Because the motion of air causes sweat on your brow to evaporate, and that cools you off. That's also the reason why when you leave a swimming pool, you feel cold. Ever notice that it's actually colder outside the swimming pool than inside the swimming pool? That violates common sense, right? That's nonsense. But that's what you feel when you leave a swimming pool. And why is that? Because when you leave a swimming pool, the contact with the air causes wind. Wind evaporates the sweat and the water on your body, cooling your body. And that's why you're actually colder outside the swimming pool than inside the swimming pool. So anyway, on a hot day, when you fan yourself, you get relief. Your head feels cool, and you have a lot of sense organs in your head, and it feels good. But ultimately, it's self-defeating. Why is that? Because of the second law of thermodynamics. Mechanical motion creates heat. And so it turns out that your body temperature rises a little bit. The air around you, its temperature rises a bit. And yes, heat is generated by the fact that you fan yourself. Now, does that mean you should stop fanning yourself? No, because you want that relief. You have a lot of sense organs in your face, and the sense organs love the fact that it's being cooled down. So that's instant relief by fanning your face. But in the long term, are you hotter than before? The answer is yes. Sorry about that. That's physics for you. Okay, let's move right along now to the next listener phone call.
My name is Jerry. I'm calling from Pasadena, California. And my question is, the string theory, does it relate to harmonics? And if it does it relate to fractal geometry? In essence, the building blocks. Thank you very much.
Okay, well, you asked several things, so let's try to break them down one by one. First of all, what is string theory? String theory, we think, though we cannot yet prove, is the theory of everything. It's a theory that eluded Einstein for the last 30 years of his life. Einstein dedicated the latter part of his life to create an equation, perhaps no more than 1 inch long, that would allow him to, quote, read the mind of God. In other words, one equation that summarizes all the laws of nature into a single theory. Well, he failed. He failed for several reasons. One is that the nuclear force was not known back in the 1930s and 40s. The nuclear force wouldn't be worked out till the 1970s and 1980s. So you can't blame Einstein for missing a huge part of the theory of everything, that is the nuclear force, because the nuclear force wouldn't be worked out for another 30 years. And what comes out of the nuclear force? Well, we have something called quarks. Quarks make up the proton, but what holds the quarks together? Strings. So strings-like things hold the quarks together inside the proton. Now, if strings are fundamental to the nuclear force, then why not use strings as a paradigm to unify all the laws of nature? And that's where string theory comes in. Strings can not only unify the nature of quarks and give us protons and neutrons, but it can do much more than that. It could give us all the subatomic particles. So the subatomic particles we see in nature, are nothing but the harmonics. Nothing but the harmonics of vibrating strings. Musical notes. The musical notes of the strings are subatomic particles. And that's why we have so many subatomic particles. We have neutrons and protons and quarks and Yang-Mills particles and gluons. Why do we have so many darn particles? Because they're nothing but musical notes on a tiny, tiny vibrating string. So physics is nothing but the harmonies you can create on these vibrating strings. Chemistry is the melodies you can play on these strings. And then, what is the universe? The universe is a symphony of strings. And then, what is the mind of God that Albert Einstein spent the last 30 years of his life writing about and working on? The mind of God would be cosmic music resonating through 11-dimensional hyperspace. That would be a candidate for the mind of God. Okay, let's move right along now to the next listener phone call.
Hi, my name's Nick. I'm calling from Tennessee on 102.3. I wanted to get your thoughts on how you feel that the Great Pyramids may have been built, their correlation with Orion. Thank you very much.
Okay, well, you ask a very interesting question. There are many theories about the pyramids. However, one theory is rather intriguing. First of all, the pyramids had a purpose, and the purpose was to honor the king and to make sure that he went to heaven. Back in those days, Osiris was the god of the dead, and Osiris is associated with the constellation of Orion. There are 3 stars in the belt of Orion, as anyone knows who's ever seen the movie Men in Black. There are 3 stars in the belt of Orion. One star is slightly out of sync with regards to the other 2 stars. Now, if you look at the pyramids, what do you see? You see 3 pyramids with one pyramid slightly askew with regards to the other pyramids. Well, in other words, perhaps Orion is on the earth. Perhaps the constellation of Orion in the heavens is a blueprint for the pyramids on the planet Earth. Well, if that's true, it's a testable theory. If that's true, there are arms and legs to Orion. And sure enough, when you look at the arms and legs of the constellation Orion, you see that they do correspond to minor pyramids. And so this is a theory, who knows whether it's correct or not, that Orion is basically, the Orion constellation is on the Earth in the form of pyramids. Now, if this is true, then you can find a reason for the orientation of the pyramids. If the pyramids are aligned toward Orion, it means that in some sense they are launching pads. The long passageways of the pyramids opens up to Orion, so perhaps it was like a booster rocket. Perhaps it was a cannonball that was pointed in the direction of Orion to make sure that the soul of the king was shot to heaven. Now, of course, this is a theory. It's hard to prove, but it's rather intriguing. And the theory, once again, is that the three pyramids in Giza is nothing but a representation of Orion in outer space. Now, then the next question is, how do you build the pyramids? I had a chance to visit the pyramids once. I got invited to speak at a conference in Alexandria, and it was amazing. Once in your lifetime, on your bucket list, be sure to put the Great Pyramids. It'll blow your minds away. Something that is, well, who knows, 3, 4, 5,000 years old, still survives almost intact after so many wars, after so many empires have come and gone. Now, how do you build it? Well, we don't know for sure. However, Herodotus, the great Greek historian, visited the pyramids thousands of years ago and actually saw the wooden planks by which the stones were moved. So in other words, the stones, the limestone stones of the pyramids were probably quarried upstream from the site of Giza, and they were shipped by boat down the river from the quarry site. Then rollers, gigantic log rollers, were then taken out, and then the blocks were placed on rollers and then rolled by humans and horses into place. Now, on the Discovery Channel, they even had a program where they tried to duplicate part of this process. It's very difficult because you can't use steel. You can't use machinery. No, we're talking about using horses and your bare hands to accomplish this feat. And so their problem was to move one stone, just one stone, because of course this was for television, and they did it. They were able to use wooden logs to create a device which could move a gigantic limestone block on rollers, and they were successful in that sense. So in other words, perhaps it was technology that is not alien, not technology from outer space, but Earth technology that made possible the building of the pyramids. Now, the other thing, however, that stands out is the pyramids are constructed so that you can barely put a razor blade. You can barely put a razor blade between two blocks. Now, think about that for a moment. The ancients didn't have laser beams by which they can calculate the orientation of these blocks to within fractions of a millimeter. No, they did it by eyesight. They didn't have telescopes. They didn't have microscopes. They didn't have the optical instruments that we take for granted today. So how did they do that? Well, that I'm not sure. But yes, they were successful in terms of moving these blocks so close to each other that you could barely put a razor blade between two blocks. Absolutely amazing. Okay, let's move right on to the next listener phone call.
This is Jake, Spokane. I was just wondering, since we have landed a spacecraft on a comet already, why can't we just piggyback on that comet, either out of the solar system or within the solar system?
Oh, well, you ask a very interesting question, and in principle, it is possible. Yes, we've actually landed on a comet, and as the comet whips around the solar system, then perhaps we'll have like a guided tour of the solar system. However, there are problems, and the problem is, one is energy. It turns out that you have to have energy to sustain your device as it whips around the solar system. Eventually, the comet moves so far from the sun that there's simply not enough sunlight to energize the batteries on the device. So you're absolutely right. Some people think that asteroids are going to be the next target, a stepping stone onto Mars. In fact, President Barack Obama told NASA years ago to create a plan for a possible journey to Mars, and they concluded that the asteroids would be the most likely candidate, and they created what is called the Asteroid Redirect Mission. The Asteroid Redirect Mission is in doubt right now in terms of funding in Congress, but its goal was to have astronauts land on an asteroid and then bring that asteroid back to the planet Earth. And so the asteroid redirect program had two implications. One, it would give us the ability to, the experience necessary to manipulate asteroids. Second, one day we may mine asteroids for valuable minerals. We think that asteroids are rich in platinum-like metals, which are extremely valuable, worth trillions of dollars, in fact, on the international market. And so it's believed that we can one day perhaps begin the process of mining the asteroids. So anyway, the answer to your question is yes, this is something that we scientists are definitely looking into, and that is piggybacking on comets as they whip around the solar system. Now, unlike meteors burn up in the atmosphere and simply disappear or land on the Earth. Comets are way out in outer space and linger. They can linger for weeks at a time because they are far outside the orbit of the Earth, and eventually they go to the outer fringes of the solar system. They could teach us an awful lot if there's enough energy to power up their solar cells as they go to the outer reaches of the solar system. Okay, let's move right along now to the next listener phone call.
This is Danny from Fort Payne, Alabama, AM 1400. I've read where some physicists say there are 10 dimensions. I've heard you say there are 11. I'm wondering, why can't you have 1,000 dimensions or 1,000,000 dimensions or even an infinite number of dimensions?
Well, you ask a very interesting question that my friends often ask who are physicists. And first of all, the reason why we have a 10-dimensional or 11-dimensional theory called string theory is as follows. It turns out the theory is mathematically unstable. The mathematics falls apart. The theory gives you nonsensical results when you deviate away from 10 or 11 dimensions. It only makes sense if you have that many dimensions. Now, you can say that why not have a theory with 100, 1,000 dimensions, but then the theory starts to have what are called anomalies, divergences. The theory blows up. The theory starts to predict nonsense. So the theory, string theory, believe it or not, is the only theory known to science that selects out its own dimensionality. No other theory in the universe selects out its own dimension. These theories can work in any number of dimensions. Newton's laws, for example, with the inverse square law that we learned in high school, Newton's laws can work in any dimension. String theory is unique in the sense that it selects out its own dimension. Then the next question is, why 10 or why 11 dimensions? Well, first of all, historically, string theory has been in 10 dimensions. Recently, however, at Princeton, the physicists there realized that you can get a higher theory with membranes, i.e. beach balls, in 11 dimensions if you add one more dimension. So what's the relationship between membranes in 11 dimensions and strings in 10 dimensions? Well, if I take a beach ball and I collapse it so that all you see is a ring, I have now converted a beach ball into a string, okay, by collapsing it. That's the relationship between 11-dimensional M theory and 10-dimensional string theory. They are the same theory. So sometimes in the literature, you'll see reference to an 11-dimensional theory called M theory, M for membrane. But if you squash a membrane, what do you get? You get a circle. In other words, it is the same theory. Now, let me give you the technical reason why it selects out the dimensionality of space and time. String theory has something called supersymmetry. It predicts not just ordinary particles, but it predicts superparticles called sparticles. Sparticles are twins of ordinary particles. So you got that? We have particles and we have superparticles. In different dimensions, we have different numbers of these things. And that's why it selects out the dimensionality. The dimensionality works out perfectly in 10 and 11 dimensions. But the number of superparticles proliferates out of control if you don't have a 10 or 11 dimensional theory. In other words, it is a matching problem. It is pure mathematics. Okay, let's take the next listener phone call.
Hello, my name is Dennis from New Brighton, Pennsylvania. What is the Earth's maximum sustainable carrying capacity of humans? What number would trigger the tripping point toward human extinction, and when may that projected number be achieved? Thank you.
Well, you ask a very embarrassing question. It's perhaps one of the most important questions facing us, but we don't know the answer. Once again, really quick, we know that our universe has 3 dimensions, that is length, width, and height. But why 3? 3 is not a magic number in mathematics. 3 is a very ordinary number. In physics, we have a theory called string theory, which allows us to unify all the known laws of physics. So why don't we win the Nobel Prize for it? Because it also predicts that the universe is really 10, maybe 11 dimensional. And the question is, well, why not 13? Why not 15? Why not more dimensions? Why not an infinite number of dimensions? And the answer to that is very simple. When you start to add more dimensions, the theory starts to have what are called anomalies and divergences. The theory starts to predict nonsense. And so for the theory to be physical, it has to be mathematically consistent. But the theories that we propose are inconsistent in other dimensions. We have to match particles with superparticles. The matching does not take place correctly in other dimensions. Okay, let's move right along now to the next listener phone call.
This is Mason from Texas. I have a question on people's origins, on how black person became white, and then a black person has black, and then how an Asian person has, like, the different eye color, and then how everyone looks different, how that became in the world. Thank you.
Okay, you ask a very interesting question, and it has to do with the Ice Age. It turns out that roughly 70,000 years ago, our best number coming from genetics is that there were only a few hundred of us, maybe 1,000 of us, that survived a cataclysm. A volcano erupted in Indonesia, we think, called the Toba volcano. You can Google it. The Toba volcano, T-O-B-A, probably destroyed 99% of all humanity, leaving only a handful that migrated out of Africa. This small group of humans, only a few hundred, went on to repopulate the entire planet Earth. We're all descendants of a handful of humans which survived that cataclysmic eruption of that volcano. Now, what happened then was, of course, as you move north, you hit the Ice Age. And because of the horrendous cold and the conditions of the Ice Age, we had to adjust. First, for example, why are black people black? Because toward the equator, there's lots of ultraviolet radiation. As you move north, there, of course, is less ultraviolet radiation, but you need sunlight to make vitamin D. And so, in other words, as you go north, you no longer have to be black, but you have to allow sunlight to come in to create vitamin D, and so your skin gets lighter. And in other words, the rate of skin cancer is quite high on the equator, and melanin, which makes skin black, protects you against ultraviolet radiation, and that's why black people are black, because originally from the equatorial region, ultraviolet radiation from the sun was so intense that a lot of people came down with skin cancer. But as you move north, your skin gets lighter, because it is so dark that it doesn't allow sunlight to come in as you move north. You get lighter because you want sunlight to come in now, because you want to create vitamin D. And then the question is, why do, for example, some people have larger noses than other people? In a hot environment, you have to get rid of heat rapidly, and that's why some people have larger nostrils. The closer you get toward the equator, the larger the nostrils. Also, the height of Asian people is not so great. Asian people tend to be shorter. They have an epicanthic fold. And why is that? Because as humans evolved during the Ice Age, there was lots of wind and blizzard. You needed that extra fold, the epicanthic fold, to protect you against the blizzards. Okay, let's move right along now to the next listener phone call.
My name is Roy. I'm from Portland, Oregon. I'm listening to K970 AM. My question is it true that not only is Earth heating up, but other planets in our solar system are heating up? If this is true, then how can global warming claim that it's just the Earth that is heating up because of CO2? Thank you.
Well, you ask a very interesting question that goes to the heart of modern-day astronomy. Venus, for example, should be a tropical planet. Should be. It's closer to the sun. Many science fiction novelists in the 1950s predicted that Venus would be a tropical vacation spot for astronauts as we explore the universe. Well, boy, were we wrong. Venus is a hellhole. Venus is 900 degrees Fahrenheit, hotter than a baker's oven, hotter than the melting point of things like tin, for example. If you were to walk on the surface of Venus, it would be molten. You would sink into some of the soil of Venus because it is so hot. Why? Because its atmosphere is almost 100% carbon dioxide. Carbon dioxide is a greenhouse gas, and as a consequence, it traps sunlight. As a consequence, that's why Venus, instead of being tropical, is hellishly hot. So this is the greenhouse effect in action. In fact, we call Venus the greenhouse planet precisely because Venus is heating up. We know the mechanism, and we can test our computer programs. So we have more data points now. Instead of simply looking at the temperature of the planet Earth with regards to carbon dioxide and sunlight and things like that, we have another planet to play with, Venus, and sure enough, Venus has a runaway greenhouse effect. Now, if you look at Mars, Mars is very cold. Mars also has an atmosphere of carbon dioxide. And we now can test our computer programs on Mars as well. Computer programs tell us that Mars should actually be very cold, much colder than it is today. But it isn't. Why? The greenhouse effect. Believe it or not, Mars, because it does have an atmosphere almost completely made of carbon dioxide, it has a little bit of a greenhouse effect, which heats it up a little bit, and that's why Mars is not as hot as it could be. And so now we have not one, not two, but actually three planets where we can test our computer programs to see exactly how much temperatures rise as a consequence of carbon dioxide. Okay, well, let's move right along now to the next listener phone call.
Hi, this is John from Tampa. Dr. Kaku was talking about black holes, that instead of, I guess, the singularity forming into a dot, it turns into a ring. That it's possible that that could be a gateway, maybe from one universe to the next. And I guess my question is, okay, it's a gateway. Let's say a person falls into that ring. What happens to the matter of which he's made of? Is he going to be ripped apart and all that? Assuming he does, that is, the ring is a gateway. How is he spit out? Is he going to be the person, let's say, or is a rocket that's sent through there or a probe going to be the probe, or is it just going to be a bunch of mush?
Okay, well, the short answer is we don't know. However, we do have the mathematics, we do have computer programs, and we can postulate what might happen in this situation. First of all, most of the textbooks concerning black holes are incorrect. Most textbooks have the black hole collapsing to a dot, and as you approach this dot, you hit what is called the event horizon, a sphere which surrounds the dot, and you are spaghettified. That is, you are ripped apart, and your body becomes a noodle of neutrons and protons that eventually disintegrates as you enter the black hole. That is usually what is taught in textbooks concerning black holes. However, we have now analyzed hundreds of black holes out there, and none of them look like the description I just gave you. First of all, they're all spinning very rapidly. We've clocked them, in fact, spinning at over 1 million miles an hour. And if you look at the mathematics now, again, this is pure mathematics, this is not observation, but if you look at the mathematics that comes out of Einstein's theory, it predicts that objects like black holes should be condensing into a ring, as you mentioned, not a dot. So forget the dot. We're not talking about a ring. The ring spins very rapidly, and this solution was found in 1963 by mathematician Roy Kerr. Well, because the ring spins so rapidly, centrifugal force holds it open so it doesn't collapse on itself. Now, the ring has marvelous properties. First of all, you can go through it and not necessarily die. If the ring is big enough, the gravitational force is weak at the center, and therefore you can actually fall through the center of the ring and come out the other side of the ring. And what happens on the other side of the ring? Well, according to the math, you enter a parallel universe. It's sort of like entering an elevator. When you enter an elevator, you hit the up button, and you can get off on any floor. When you get off on any floor, you can go back into the elevator and go to another floor. That's very similar to the geometry of the Kerr spinning black hole. If you leave the black hole and come back and enter it again a second time, you enter a second parallel universe. If you go a third time, you enter a third parallel universe. And so it's like going up the floors of an apartment building using an elevator. Now, that's the mathematics. What does the physics say? Well, unfortunately, the physics doesn't tell us much because we do not yet have a good feeling for what happens inside the event horizon. On the planet Earth today, at Caltech, they're trying to lead a group to create the world's largest radio telescope to give us the first photograph of the event horizon. It lashes together many radio telescopes to give us an effective radio telescope roughly the size of the planet Earth. We expect numbers to come from this in the next few years. Watch for it. That is, real numbers about the heart of a black hole from a radio telescope effectively the size of the planet Earth. Well, unfortunately, we have run out of time in this segment of Science Fantastic.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping, scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, it's time for you. Okay, let's move right on to the next listener phone call.
This is Gloria, Pottstown, Pennsylvania, WEEU. I was wondering, with these black holes, why can they not rig up a probe and send it into the black hole with a camera? Pretty much like they have those on-man things with the Army, that they can take pictures, send it back, and then we can find out more of what is going on in the black hole. Thank you. Bye-bye.
Well, you ask an excellent question. First of all, we do exactly that to the planets and the moons. We take a camera, put it onto a rocket, and we actually send them into Jupiter and Saturn and different places around the solar system. And as a consequence, we know an awful lot about atmospheres, about the surface, about the structure of the planets because we have probes with cameras. However, when you talk about black holes, there's a catch. There's always a catch someplace. First of all, the nearest black hole is many light years away. For example, we have a raging black hole at the center of the Milky Way galaxy. Tonight, if you go outside, look in the direction of Sagittarius. In that direction, there should be, by rights, a fireball. There should be a fireball there, which is the galactic nucleus, the center of the galaxy. You can't see this fireball because it's obscured by dust clouds, and the disk of the galaxy, yes, has lots of dust. In fact, that's where we come from. We are made out of galactic dust. But it's a nuisance if you want to see the center of the Milky Way galaxy. At the very center, there's a raging black hole. It weighs 2 million times the mass of the sun. So what's the problem? The problem is these black holes are located hundreds, thousands of light years away, and each light year is about 6 trillion miles. So in other words, we're not going to go to any black hole anytime soon. They're simply too far because the universe is too big. Now, that doesn't prevent us from dreaming about sending a probe or a camera into a black hole. Now, the next best thing you can do is to get a computer to simulate Einstein's equations for a black hole. And we've done that. If you saw the movie Interstellar, starring Matthew McConaughey, they actually take a rocket and go through the gateway, the wormhole, to a black hole. And using computers and Einstein's equations, you can actually see what a hypothetical journey would look like. All sorts of bizarre things happen when you fall through the wormhole connecting you to the black hole to perhaps maybe another universe. So if you see the movie Interstellar, it gives you the best computer rendition of traveling through a black hole, because the nearest black hole is simply too far away, trillions upon trillions of light years, and we're not going to go that distance anytime soon. Okay, let's move on to the next listener phone call.
Hi, my name is Jen. My question was, how many monkeys have to evolve to create a whole other species?
Well, that number depends upon the circumstances and the species you're talking about. First of all, we have to even define what a species is and how we tell two species apart. And this is where biology starts to get a little bit of fuzzy, even in the definitions of species. Usually biology books say that when two groups of organisms can no longer mate and produce viable progeny, that's when these two groups have separated, and they have speciated, and they're no longer part of one species. Okay? Now, there's lots of ambiguity. Okay? For example, what about the donkey and the mule? And what about the liger? The liger is a cross between a tiger and a lion. Believe it or not, you can mate a tiger and a lion and come out with a liger. So, how do you define two different species, given the fact that they can, in fact, mate and produce progeny? But these progenies are usually sterile. Therefore, you cannot create a third distinct species by mating two species, even though they are very close. Now, take a look at our own species, the Neanderthals, for example. Most people would say, and many biologists would say, that the Neanderthal is a separate species from humans. How come we know that? Because we can't mate with them. Well, that's been disproven. In fact, on our airwaves, I've actually interviewed the man who did it. The man who took Neanderthal skeletons, about 6 of them, and extracted usable DNA from the Neanderthals, and from that created a composite genome. That's incredible. A composite genome of the Neanderthal man. And the Neanderthals, do they constitute a new species, different from us? And the answer apparently is, well, we don't know. Maybe no, because according to the person I interviewed, he sequenced the genes and found there is about a 1% overlap. Incredible. A 1% overlap between our DNA and Neanderthal DNA. So in other words, our ancestors mated with them. This is rather shocking, because we used to think that Homo sapiens are all high and mighty and that we are unique and that we're at the top of the evolutionary chain, and we now realize that we share DNA with the Neanderthals. In fact, certain characteristics that we shared are very interesting. One of them is to withstand cold climates. It turns out that Neanderthal DNA might have been useful because the Neanderthals lived in iced areas of northern Europe much longer than we did, and they were better adapted to the Ice Age than Homo sapiens. Also, he said, certain characteristics may be traced to the Neanderthals. For example, red hair. There's indication, even though it's not conclusive yet, he said, there are indications that red hair is a byproduct of mating with the Neanderthal. And so to sum up, usually biology books say that you have to speciate when you can no longer mate with the other species. But then what about the Neanderthal? Okay, let's move right on to the next listener phone call.
I'm calling from Sterling, Massachusetts. My question is about the cosmic background radiation, which is due to the Big Bang. The background radiation is continuous, and the Big Bang was an explosion. So could you resolve that paradox? Thank you.
Okay, first let's define some terms. First of all, when you turn on your radio, you of course get static if you're between stations. Where does that static come from? Well, it turns out that a lot of it comes from Jupiter. Believe it or not, Jupiter is quite radioactive, quite energetic, and we now know that a fair amount of the static you pick up on radio comes from the planet Jupiter. What about the other pieces of static? Well, some of it comes from the Big Bang. Genesis, the origin of the universe. You're actually listening in on remnants, an aftershock, the afterglow of the creation of the universe itself. So how does that work? Well, as the gentleman pointed out, the Big Bang was just basically one gigantic fireball that erupted, and gradually over time it began to cool off and created the stars and the galaxies that we see around us. However, about 300,000 years after the Big Bang, there was a very important event that happened, and that is that atoms could form for the first time. You see, before 300,000 years ago, before the incident of the Big Bang, out to 300,000 years, it was too hot. The universe was too hot. The universe was opaque. You could not see very far if you were alive during that time. The universe was very opaque, and it was cool enough 300,000 years after the Big Bang for atoms to condense, for electrons to go around hydrogen. That point is the radiation picked up by our satellites. It's the radiation picked up by your radio. So your radio is picking up radiation 300,000 years after the instant of creation. And that resolves the problem. The gentleman asked the question, the cosmic background radiation is smooth, but the Big Bang was a violent event. How do you reconcile the two? Well, the Big Bang came first. It was that violent event which sent all the gaseous materials out into outer space, but it took time. It took time for that gaseous fireball to cool down to the point where atoms can form. At that point, space becomes transparent. Now, we've always thought of empty space as being a description of the universe, but that's not always true. In the first 300,000 years of our infant universe life, the universe was basically opaque. You couldn't see very far. 300,000 years after the Big Bang, the first atoms began to condense. The familiar atoms, hydrogen and helium, lithium, began to condense out of the primordial gas that came out of the Big Bang. And that primordial radiation, 300,000 years after creation, as atoms were condensing, that is what you pick up when you look at the cosmic microwave background, which is the echo of the Big Bang. Not the Big Bang itself. It's the echo of the Big Bang 300,000 years after the instant of creation. Okay, well, let's move right along now to the next listener phone call.
Hi, this is Paula. I'm calling from Camdenton, Missouri, and I would like to ask, how long does it take for a stem cell and tissue to form an ear? How long does it take from start to finish to put together the ear or any other part? Thank you very much.
Okay, well, first of all, let me explain how we do it, and then I'll ask you a question of how long does it take. First of all, stem cell technology is very primitive, not that advanced, but not even using cells that are not stem cells, scientists at Wake Forest University have been able to create all sorts of human organs, not just the ear. At the present time, not even using stem cells, ordinary cells that have been treated specially, we can create carbon copies made out of plastic of ears, noses, cartilage, skin, blood vessels, heart valves, bladders, and windpipes. That is incredible. It's almost like walking through Frankenstein's laboratory. I had a chance to take a film crew from the Discovery Channel. We flew down to Wake Forest University in North Carolina, and we visited the laboratory of Anthony Ataya. Maybe you've seen some of his work on science specials, and you sort of feel like, feel like Frankenstein's doctor walking through the hallway at Wake Forest University, looking at jars containing human organs, human hearts, human livers. Kind of eerie. But then you realize that, these are mock-ups. These are practice attempts to create kidneys and livers and hearts. Because right now we can't do that. Right now we can basically create tissues made out of basically one type of tissue. However, the liver and other organs of the body require many different kinds of tissues, and that's where it takes time. Now, the caller asked, first of all, how long does it take to grow an organ? The answer is a few weeks. You can grow a whole ear in about 2 or 3 weeks in the laboratory. In fact, there's even the program that I hosted for the Discovery Channel called 2057, talking about the future, where we actually visit these laboratories and interact with the scientists who are, in fact, creating bodies of the future. Now, to create a clone of the brain, of course, takes a lot more effort, but it turns out that already with today's technology, we can already begin the process of creating organs that are almost indistinguishable from human skin, bone, cartilage, noses, ears, heart valves, and bladders, and even windpipes. Truly miraculous. Okay, let's move right along to the next listener phone call.
Hi, my name is Rick. I'm calling from Interstate 15 south of Las Vegas, driving a truck. My question is a neutron bomb a neutrino emitter, or does it create neutrinos? If so, if you have a neutrino detector and you are setting off a neutrino emitter, wouldn't you be able to detect things on the other side of whatever it is you're trying to look into, such as you suggested the Earth?
Well, first of all, let's talk about the neutron bomb, and then let's talk about neutrinos. First of all, the N of the neutron bomb does not mean neutrino. It means neutron. It is a neutron bomb, not a neutrino bomb. In fact, in physics, we use the neutrino bomb as a joke, because if a neutrino bomb goes off, what happens? Nothing. Absolutely nothing. Because your body is being penetrated by billions upon billions of neutrinos from the sun, black holes, and whatever, and you don't feel a thing. Neutrinos, in fact, can go through light years of lead, and not even get absorbed. That's incredible. Think of our solar system made out of solid lead, and you can shoot a beam of neutrinos right through it. So a neutron bomb, the N stands for neutrons. They, in turn, can do a lot of damage. A lot of the damage from bombs actually comes from neutrons. So the N bomb, the neutron bomb, neutrons do cause a lot of damage. And so the neutrino is emitted as a byproduct of the fusion process, but the neutrinos are extremely ephemerate. That is, they go right through matter without hardly noticing it. And that means you can send it right through the center of the Earth. One day, perhaps we'll have neutrino detectors that can detect earthquakes on the other side of the Earth, because they go right through the Earth as if the Earth is made out of nothing. So neutrinos are quite different from neutrons. First of all, hydrogen bombs have gone through 3 different stages. Stage 1 of a hydrogen bomb, they were so big, gigantic, that they had to be placed on a ship in order to deliver it to its target. So the first generation hydrogen bombs were kind of useless in terms of warfare. They were built in the 1950s, huge, gigantic bombs, 1,000 times more powerful than the Hiroshima bomb, but they were so big and clumsy that you couldn't use them in an actual war. Second generation hydrogen bombs are hydrogen bombs which are MIRVs, small, compact, and you can put 10 of them in the nose cone of a Minuteman missile. These are called Type 2 hydrogen bombs. Then there are Type 3 hydrogen bombs, which are designer hydrogen bombs that are used for a particular purpose, like to be used in the battlefield, in the desert, in the jungle, in the North Pole, in outer space. Star Wars type weapons would be a typical Type 3 hydrogen bomb. Then there's a neutron bomb. It's a 2.5 generation bomb. It's halfway between a MIRV and a designer hydrogen warhead. So the neutron bomb is a 2.5 generation bomb. Now, how dangerous is it? Well, the neutron bomb is sometimes called the landlord's bomb. Because if a landlord wants to evict the tenants, you want to preserve private property, but kick the tenants out. Well, that's what the neutron bomb does. The neutron bomb goes right through houses. It goes right through inert material. But when it hits tissue, it hits human flesh, it destroys it, causing mutations, causing burns, and things like that. And so that's why they call the neutron bomb the landlord's bomb, because it's a clever way to evict the tenants by vaporizing them, but without hurting your private property. And that, of course, is, again, different from the neutrinos, which are very elusive. They can go right through the center of the Earth. At this very minute, right now, as you're listening to this radio show, You are being hit by neutrinos coming from the ground because they came from a black hole on the other side of the universe. So think about this. Right now, you're being hit by radiation coming from the ground going up through your body, and that is how elusive the neutrino is. Now, why use it? Because one day we may have neutrino telescopes that may give us pictures of the inside of the Earth. X-rays can't do it. Neutrons can't do it. They cannot penetrate. They cannot penetrate to the center of the Earth, but neutrino telescopes can. So what's the catch? The catch is that neutrinos are so elusive that you can go right through the entire Earth and not hit anything at all. So therefore, neutrino telescopes, even though it's a great idea, are not practical because they're simply too penetrating. Okay, let's take the next listener phone call.
Trevor from Eager, Arizona, 1400 AM, and I'd like to know if there's a boundary to the universe, because the stars, there's places where we see no stars, and it's just black. And I'd like to know if there is a boundary to the universe.
Well, you ask a little bit of an embarrassing question, because the short answer is we're not really sure. However, we do know that the universe is more mysterious than we thought. First of all, there are these black spotches where there's simply no stars at all. Now, the Big Bang Theory says that the universe should be uniform. No matter where you look, you should see even density. But we do have these splotches out there. Some people think they're remnants of a colliding universe. So I'll talk about that after the break. But yes, perhaps evidence of a parallel universe that has been picked up by our satellites. Okay, let's take a short commercial break. Once again, you are listening to Science Fantastic. And after the break, we're going to talk about collisions with parallel universes. Yes, some physicists are taking this very seriously. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a call about, well, how come there are blank spotches in the universe, places where there are no stars? This is rather embarrassing for us because the universe should be uniform, according to the Big Bang Theory. So how come the universe has these holes in it where there are no stars? Well, the short answer is we don't know. But there's a theory that says that maybe it's the scar left over from colliding with a parallel universe. This is taken actually very seriously. I've seen talks on this. Because the leading theory of the Big Bang is called inflation, proposed by my colleague, Alan Guth of MIT. And in inflation theory, the universe blew up in a Big Bang, but Big Bangs can happen more than once. And in fact, they happen all the time. Each time a Big Bang happens, it creates a baby universe that has budded from our universe. Well, if you can have universes budding from our universes, then obviously you can also have universes colliding with other universes, and that may explain some of these black splotches. Maybe they are remnants of an ancient collision that we had with another parallel universe. So we now believe that our universe is a bubble, but this bubble can have baby bubbles, and it could have parallel bubbles. And when these bubbles collide, or when these bubbles peel off baby universes, then that's why we have the Big Bang. In other words, the Big Bang is probably the remnant of an ancient collision with another universe, or perhaps it's the budding of our universe into a baby universe. All of this, of course, is theory, but these theories are being taken very seriously. And then the caller asks another question: where is the boundary of the universe? Well, if the universe is a bubble, and we live on the skin of the bubble, then the bubble has no boundary. In other words, in 2 dimensions, a bubble is infinite. You can go around the bubble an infinite number of times and never meet the end of the bubble, because, of course, it is a bubble. So a bubble in 2 dimensions is infinite. But in 3 dimensions, obviously, is finite. It's a bubble, for God's sake. So that's how you get around the fact that you have a universe with no boundary. So we don't think the universe has a boundary. That would violate Einstein's equations, which says the universe must be smooth like a sheet of paper or like a trampoline net. And having a boundary would violate that principle. So in other words, to answer your question, the universe probably has no boundary at all. The boundary, if it does exist, exists in another dimension, a dimension we cannot see, a dimension that swallows up our universe. So our universe could be a bubble floating in a higher dimension. Okay, well, let's move right along to the next listener phone call.
Hi, my name's Alan from Austin, Texas, and I'm listening through the internet. And my question is, as far as wind energy goes, why can't they, the big problem is storage or transmission. Why can't they use the wind to convert water into hydrogen at the location and then transport the hydrogen and use that for energy somewhere else?
Well, you ask a very interesting question because in principle, yes, everything you just said is doable, but there's always a catch, right? The catch is cost and inefficiency. You see, every time you convert one form of energy into another form of energy, you lose some energy. That's called the second law of thermodynamics. It means that there's always waste heat generated because you're transforming energy from one form to another. Therefore, you have to worry about losses. You have losses every time you transfer energy from one form to the other. Hydrogen, you can ship and use that for times when, let's say, the sun doesn't shine or the winds don't blow. Well, yes, you can do that, but the problem is you lose energy every time you convert energy from one form to another. So, for example, to convert wind to electricity, yes, you can do that. You lose a little bit of energy there. Electricity that can then be used to break up water for electrolysis, that takes waste energy. And then you can use that to transport hydrogen. Sounds great, but you lose energy every time you make that conversion process. And that's the basic problem. Let me give you another example of how waste energy determined the nature of the power grid. About 100 years ago or so, Nikola Tesla and Thomas Edison had a rivalry, and that was would AC or DC transmit energy. Tesla said AC, and that's what we use today. We have 60-cycle AC power in our home. Edison said no, direct current. Electrons moving in one direction, not going back and forth, back and forth. Well, who was right? Well, obviously, Tesla was right. But why was Tesla right? Because of energy loss. It turns out that AC current can travel longer distances and have less waste energy than DC. In other words, it's economics. The economics eventually killed Edison's idea of direct current. People call that the battle of the currents, or the battle of the geniuses, Nikola Tesla versus Thomas Edison. Both, of course, were giants in their field. So, the same thing with wind power and solar power. We want to have as few translations of energy from one form into another as possible, because each time you do that, you lose energy. So the leading way to do it, I think, is with ordinary batteries. If the sun don't shine, you want to have batteries that can store energy so that at nighttime you can use the electricity stored. Utilities will love that, because if we have super batteries, like what Elon Musk is proposing, then we don't have to have power plants that have to go to peak power and produce peak winter energy. It's a waste of time, because most of the time a power plant is not using peak power consumption or peak winter. So what's the way to smooth out the energy cycle? Batteries. But batteries are getting more efficient every year. Battery prices drop about 17% a year. Tremendous drop in the price of batteries, meaning that in the future, batteries could be the way to go. Okay, let's take the next listener phone call.
This is Jay in Kansas City. I was wondering if you might explain a little bit about how integral fast reactors work and maybe comment on their safety. Thank you, Doc.
Okay, well, we have with us today light water reactors that use uranium and are cooled by water. You got that? So these are the commercial reactors that we see today. However, there's another kind of reactor called hard nuclear reactor, which is based on plutonium. And they are fast reactors. Fast meaning the speed of the neutron. Now, why is there some concern about plutonium-fired fast reactors? Because plutonium is much easier to detonate off of than the uranium that we use. The uranium that we use in reactors today is 3% enriched uranium. That's too low. It turns out that bomb-grade uranium has to be enriched to 90% in order to make an atomic bomb. Therefore, commercial reactors of today, the uranium is simply not usable for a bomb. So fast reactors have also been looked at. Fast reactors, in some sense, create plutonium as well as use plutonium. They call it the Midas touch. Midas was the king who, when he touched anything, it turned to gold. However, one day he touched his daughter, and his daughter turned to gold. So there was a downside to that ability. So fast reactors, well, they operate on plutonium, not uranium, and they are recyclable. That is, you can create plutonium as well as use plutonium. So it's like the Midas touch, something for nothing. Well, of course, in nature, there's no such thing as something for nothing. That would also violate the second law of thermodynamics. So what's the catch? What's the catch with regards to fast reactors? And that is you can detonate on them. You can actually build atomic bombs because the threshold for the purification of plutonium is a lot lower than the threshold for purifying uranium. Uranium has to be purified from 3% to 90%. That's what the Iranians are trying to do, by the way. They, of course, would like to go to bomb-grade uranium. Well, unfortunately, our time is up. Good day.